There's a few reasons why BGP is the protocol of the internet. Maybe the main reason that BGP is the protocol of the internet, that's what's exchanging hundreds of thousands of routes every day around the world, is because it scales so well. But here's the thing, here's the secret. By default, it doesn't scale so well. There are some nuances, again, about BGP that you really need to understand so that you can configure BGP to scale so well, and that's what this skill is all about. We need to talk about the different scenarios that eBGP and iBGP operate differently. And then we need to talk about how we can build a scalable solution with BGP using things like route reflectors and confederations. So that's what this skill is all about. It's going to be a lot of fun. Get ready to fire up the virtual lab, and let's get going. You're actually going to get a 2-for-1 in this nugget. There's two major nuances that differentiate eBGP from iBGP, and that's what we're going to cover in this nugget. The first nuance that we're going to talk about is how eBGP shares learned routes versus how iBGP shares learned routes. And then that will feed into a discussion about what's called multi-hop. Let's jump on a whiteboard and I'll draw it up for you. How eBGP and iBGP share learned routes is a critical functionality to master, or it's one that you're going to be caught off guard majorly when it comes time to implement a network that runs BGP. To refresh your memory, you can see here that we have an eBGP link from AS200 to AS100. So as R4 is advertising routes towards AS200, because it's an eBGP relationship, it's changing the next hop address. So as a route leaves an AS, it changes the next hop address. But as a route gets shared within an autonomous system, the next hop address doesn't change. That was a pretty major nuance when we looked at the difference between eBGP and iBGP. Now we need to talk about when a route is even advertised in the first place. When it comes to eBGP, routes get advertised in a couple different situations. So here I'm going to write eBGP, a little underline, and we'll say number one is when we use a network statement. If we use a network statement, we are telling our router, you need to advertise this network. So maybe R4 here has a loopback of 4.4.4.4. We use a network statement to advertise it. It will advertise it out its eBGP link down to AS100, and of course it will set the next hop address towards that. The second time that networks get advertised out eBGP links is when we've received a valid NLRI. Remember, that is a prefix as well as path attributes. So regardless of where R4 learns about its network, maybe it receives one coming in from an eBGP link coming from this way, or it receives a network coming in from iBGP, it's going to advertise it out the eBGP link unless we have a policy that stops it from doing that. iBGP is a little bit different and in a pretty major way. Now pretend for a moment that R1 has a loopback of 1.1.1.1, and we issue the network statement on that device. Well, the first thing, the network statement here means that we're going to advertise this towards all peers, regardless of eBGP or iBGP. But the next spot is where it gets really important. R2 receives a valid route towards R1, and with no policies, it will forward it out the eBGP link, but it will not forward it to other iBGP peers. So I'm going to put 2 here and say only eBGP for valid NLRIs. This is a major nuance between iBGP and eBGP. The fact that you can learn an iBGP route from a peer, but you will not forward it to any other iBGP peers. It will only ever get forwarded out to eBGP unless we set up some other things like route reflectors. And that's what we're going to talk about later. For now, this sets up the conversation about how do we then get R3 and R11 to learn about 1.1.1.1. R1 here has issued the network statement 1.1.1.1, so the next solution to make sure they learn about this is to build peering relationships to each of these devices. In fact, we need to mention this right now. The only way that you can get full connectivity in this autonomous system using BGP is if you had a full mesh. Yeah, you see all of these links all of a sudden, they're going everywhere? That's right. And that's going to play a bigger factor when we get down the road. But let's talk about this for a second, which brings up our next major nuance between eBGP and iBGP. In order for R1 to connect to R3 and form a BGP relationship, first of all, we have to have routability between them. So either static routes or more likely an IGP will be running, like OSPF or EIGRP. So the next thing we need to think about is the actual mechanisms that take place. When you issue the neighbor statement, what happens? Pretend we're on R1 for a second, and we issue the neighbor statement for R3. R1 is building a packet sourced out of gig 10 here, destined for R3, and it's going towards TCP port 179. As the packet leaves R1, it's going to arrive on R2. R2 goes up to layer 3, looks at its routing table, says, I know how to get to R3, and forwards it along. It never looks at layer 4, and it doesn't care that there's a BGP relationship going on the other sides of it. It's just a transit router at this point. But what also goes on in a TCP header is something called the TTL, the time to live. A fancy way of saying how many hops can this packet go before we determine that this packet is dead. And this is the next major difference between eBGP and iBGP. The screen's getting a little messy, so at this point I'm going to clear it. And we're going to say when R1 wants to communicate to R2 and then to R3 to form its BGP relationship with R3, this TTL will need to be big enough to allow these hops to occur. In iBGP, the TTL is set to 255. So our open packet, when we try to form a BGP session, is allowed to hop from one device to the next device in an iBGP session. In an eBGP session, the TTL is set to 0. That's right. eBGP sessions, by default, have to be directly connected. Even if R2 wanted to peer with the loopback address of R4, let's call that 4.4.4.4, that would be a hop to this interface and then routed to R4. This is called multi-hop. And knowing the difference between an iBGP multi-hop scenario, basically multi-hop is allowed, versus an eBGP multi-hop scenario, basically multi-hop is not allowed, it's going to be important for you to understand too. So what we're going to do now is we're going to jump in the virtual lab and we are going to build this topology. We're going to build a full mesh AS100 and then we're going to build a multi-hop connection to the loopback address on R4. Let's get going. Now, to reemphasize some of the key topics here that we covered in the previous section when we were setting up the basics of BGP, I'm going to build a topology where there's R1, R2, R3, and R11 down here. These are all within AS100, and I'm going to build this full mesh topology, so R1 will have a connection here, R1 will have a connection here, R2 is already pretty well meshed, and R3 just needs a connection to R11 at this point. But I'm going to build this so that it's peered based on loopback addresses. Immediately, that should be signaling that this is going to be a multi-hop situation because we have to hop to get to even the closest loopback address. Because iBGP allows that, I'm not going to run into any issues. Where I'm going to run into an issue is when we get up here to R4 and I want to peer with the loopback address of 4.4.4.4. Now, typically, you would not peer with a remote device's loopback address. This is just to set up how eBGP multi-hop really works. So my challenge to you is fire up the virtual lab and get AS100 already up and running and configured. Then we can start talking about the eBGP multi-hop. And after just a few moments, I have my AS100 topology completely stood up. I ran OSPF to bring all the interfaces and routability into AS100. That way there's an IGP running and everybody can reach everybody. Then I was able to issue my neighbor commands. I went into the address family configuration mode, activated them, made sure I did the update source to loopback 1. Now I can do show BGP IPv4 unicast summary. Got to use an M there. And now I see that I've got my neighbor relationships right up here on R11. There aren't sharing any prefixes at this point. That's fine. We're just showing that multi-hop worked perfectly fine in an iBGP scenario. So now what we need to do is we need to jump over to R2 and make sure we get into router BGP 100 and start to try to bring up the BGP relationship with R4's loopback address 4.4.4.4. If I say neighbor 4.4.4.4 remote AS of 200, it instantly knows This is an eBGP relationship. It also doesn't have a route to 4.4.4.4 currently, so it's immediately not even trying to form that relationship. I will go into address family IPv4 and activate this relationship. We'll say neighbor 4.4.4.4, activate. And then I'll exit out of router configuration mode and quickly give myself a static route to 4.4.4.4, going out that outbound interface, just like that. So at this point, our router is trying to reach 4.4.4.4, sourcing the TCP packet from 100.100.24.2. See, now it's looking in the route table for 4.4.4.4, and it sees that it's outbound towards this locally connected interface. So R4, when we issue the neighbor statement, would be expecting a neighbor of that IP address. Let's go try to bring that neighbor relationship alive. We'll go to router BGP 200, and we'll say our neighbor is going to be 100.100.24.2 in the remote AS of 100. Now here's the thing. We would expect this neighbor relationship to come to life at this point. See, I can ping the remote address here. Looks good. And from R2, I can ping the loopback address, so there's reachability, there's connectivity, but it's not coming to life because eBGP multi-hop stops this from happening. So what we have to do to make this work is we have to configure eBGP multi-hop. So I'll jump back into router configuration mode, and I'll specify for my neighbor of 4.4.4.4, there's a couple options that we have here. The first one is disable connected check. This allows for a one hop away eBGP peer using a loopback address. There's also eBGP multi-hop, allow eBGP neighbors not on directly connected networks. So I'm going to do disable connected check first. Then for neighbor 4.4.4, and look at that. That's all it took to make this neighbor relationship come to life. For good measure, though, I can also run the command 4.4.4.4 eBGP multi-hop, and then the next thing it asks for is what is the time to live? How many hops are we going to allow for this packet? I'll put something like 10 for now, even though the neighbor relationship is up and running. So if I say end, and now I do a show BGP IPv4 unicast summary, there. Now I see I'm paired with the loopback address eBGP AS200. So that's the nuance, the difference between eBGP and iBGP when it comes to multi-hop, but this sets up the real scenario that we're here to talk to. We did this with only 4 routers. How many BGP sessions are actually active right here? The formula is the number of routers times the number of routers minus 1 divided by 2. In this case, that's 4 times 4 minus 1 divided by 2. So we've got 12 divided by 2. There are 6 BGP sessions active right now. Imagine for a second now that there are 10,000 routers. Yeah, you get the idea. The number of BGP sessions that we're working with here is now absolutely astronomical. We're looking at hundreds of thousands of BGP sessions, and all of a sudden, this full mesh topology to make iBGP work is not scalable. This is too many BGP sessions. How we fix the iBGP full mesh scalability problem, we can do it first with something called route reflectors, and that's what the next nugget's all about. In the meantime, that's been setting up multi-hop and the scaling issue that we're trying to solve. I hope this has been informative for you, and I'd like to thank you for viewing. So now at this point, we've seen how iBGP can get around the fact that it doesn't forward network prefixes or NLRIs to other iBGP peers. We've seen how we can get around that by implementing a full mesh topology. But the formula showed us pretty quickly that that full mesh topology is not realistic for service providers because there would be way too many BGP sessions flapping all the time, or it would just overwhelm routers in the first place. So how we can fix this is with something called route reflectors. And there's 3 rules to how route reflectors work in an iBGP solution. That's what this nugget's going to set up, is what is rule number 1 and how do route reflectors really work. Let's jump on a whiteboard and draw it up. So our iBGP topology for AS100 looks like this currently. And this is a perfect scenario of how we can use route reflectors. So to recap, what happened is when R1 advertised a route to R2, or R3 advertised a route to R2, or R11 advertised a route to R2, that's where the buck stopped. R2 is not going to forward any prefixes or NLRIs in an iBGP topology because iBGP does not forward internally learned routes. What we may want to have happen, though, is we may want routes to come in from one of these devices. R2 learns about them and then reflects them on to more devices. So let's say R3 advertises its loopback address into IBGP. R2 could then learn about it and then reflect it on to other routers in its IBGP peer table. In this case, R2 is called, wait, you guessed it, the route reflector. But again, BGP is a deliberate protocol, so we have to choose where routes get reflected to. In this case, let's call R1 the route reflector client. Luckily for us, the configuration of route reflectors is extremely simple, but the behavior of route reflectors is a little bit complicated. And that's why we have 3 rules, or really 3 different scenarios as to how a route reflector will work. In this case, we're talking about rule number 1, where R2 is serving as the route reflector and R1 is the route reflector client. R3 is not a route reflector client, and R11 is not a route reflector client. Even though R2 has an IBGP relationship with it, the way it handles a client versus a non-client is what matters here. So in rule 1, when R3 advertises 3.3.3.3, the rule looks like this. R2 will send routes learned from non-clients to clients only. So R3 will advertise 3.3.3.3. R2 will then forward this to its client of R1. It will not forward it down to R11. So this sets up rule 1, what to do when a route reflector receives a route from a non-client. In this case, it will forward it to clients only. That's rule 1, and in the next nugget, we're going to implement this topology. In the meantime, I hope this has been informative for you, and I'd like to thank you for viewing. Now it's time to fire up the virtual lab and see rule 1 of route reflectors in action. My challenge to you is fire up the virtual lab and just get basic neighbor relationships set up to R2. Don't build a full topology yet, because that is what route reflectors looks to save. So here I am on R2. I can give it a show BGP IPv4 unicast summary, and we'll see pretty quickly I have neighbor relationships with 1.1.1.1, 3.3.3.3, 11.11.11.11. Let's jump over to R3 for a second. Let me bounce out of configuration mode, give it a show BGP IPv4 unicast summary one more time. It only has a neighbor relationship to R2. Let's advertise an NLRA of our loopback address 3.3.3.3 towards R2. I'll go into router BGP 100, and I'll specify my network of 3.3.3.3, mask of 255.255.255.255, and at this point, it should be advertising the 3.3.3.3 network towards R2. If I bounce out, I can go to R2. I'll run the exact same command again, showing that summary, and I see that now I've received a prefix. So at this point, I would expect that none of the other neighbors, 11 or 1, have received that prefix. Let's give it a show BGP IPv4 unicast summary, and I see here I've got a neighbor relationship with 2222, but I'm not receiving any advertised NLRIs. Does R11 hold the same truth to it? Let's do show BGP IPv4 unicast summary. And sure enough, there's my neighbor relationship with 2222, but no prefix is received. That illustrates that rule of IBGP that none of these routes will be forwarded along unless we configure a route reflector. So in our scenario, we had R3 here, paired with R2, and we wanted it to bounce routes learned from R3 over to R1. There was also R11. So R1 will be our client, R2 will be our route reflector, and these, R3 and R11, will be non-clients. And Rule 1 specified that when R3 advertised a route, a non-client advertised a route, it would only be forwarded into clients. So to configure R1 as a client from R2, we'll go into configuration mode. We'll say router BGP 100, that's our instance. And all we have to do is say neighbor 1.1.1.1 route reflector client. Hit enter, and that's it. Look at that. It bounces the topology though. You see, we've had an adjacency change, and now the neighbor relationship comes back up. I'll exit out of configuration mode, and I'll give it a show BGP IPv4 unicast neighbor 1.1.1.1. And now if I scroll down just a hair in the second section for address family IPv4 unicast, we can see that we've configured neighbor 1.1.1 as a route reflector client. This is another key talking point. Route reflectors are configured for each address family. So just because we configured 1.1.1.1 as a route reflector client, it's only applied to IPv4. If we also wanted to apply that to, say, IPv6, we would have to go into that address family and fix that up. Let's go back to R1 for a second and let's check out the summary one more time. Now I see that I've got a prefix that's being advertised to me. If I give it a show BGP IPv4 unicast without the summary, I see the route that's being sent here is 3.3.3.3. Interestingly, though, it's not installed in the IP routing table because we had a, what's the code right here? A rib failure. Look at that next hop. The next hop is the address that we learned after all, because we set the source updates to be 3333, and that's what gets advertised out. Another nuance of BGP that you need to know. When you do an update source command, that's the route that it's going to advertise as the next hop. So what we could do to fix this is we could use a route map, which we're going to talk about in a later series of skills. And that's really what you would have to do. Because I know where your head went. Your head went, oh, well, just do next hop self, right? Let's go into router BGP, 100, neighbor, 1.1.1.1, next hop self, and that should fix it. But check this out. If I go back to R1, I run this command a few more times. No, it's not updating the route. It's still not passing that rib check, is it? That's because the route reflector is a reflector. It's not advertising a route that it learned. It's literally bouncing off. So when 3.3.3.3 advertises the next hop of 3.3.3.3, it's literally bouncing off of R2 over to R1 unchanged. To fix this, we would have to use a route map to change the next hop address as it's coming in. That's going to be one of those inbound policies. But this has demonstrated part of rule number 1, which is that routes learned from non-clients are reflected to clients. Let's validate this by also checking out what's going on over at R11, another non-client. Did R11, in fact, receive a reflection from R3? Jumping over to R11 one more time, I'm going to run the summary command one more time, and you can see there it is. No prefixes received or were reflected down to a non-client. So that finishes up rule number 1. In the next nugget, we're going to talk about rule number 2. In the meantime, I hope this has been informative for you, and I'd like to thank you for viewing. There are 3 rules to working with route reflectors and route reflector clients, though. We've covered one of them. What happens when a prefix or an NLRI comes in from a non-client? Now what we need to talk about is what happens when an NLRI comes in from a client. Let's jump on the whiteboard and set up the scenario and talk about how route reflectors are going to behave. In the previous nugget, we demoed how to configure a route reflector client. From the route reflector itself, in this case R2, you simply modify your neighbor relationship with the command route reflector client. And that's it. That's all there is to configuring a route reflector. It's the behavior that really matters. We demoed what happens when R3 advertised a route in. Because it was not a client, it forwarded the route to R1. But now what we need to talk about is what happens when R1 advertises a route towards a route reflector client. What it does at this point, the route reflector will advertise this route everywhere. It will even bounce the route back to R1. Yeah, that's absolutely right. In this case, the route reflector will reflect routes towards clients and towards non-clients. Because R1 sees that it originated the route, it's going to discard it as a loop and not install it in the local routing table in the first place. So, recap. From non-clients, go towards only clients. From clients, go towards everywhere. So what we're going to do in the next nugget is we're going to jump in the virtual lab and we're going to advertise a network from R1 and verify that it shows up on our non-clients R3 and R11. In the meantime, that's been rule number 2. I hope this has been informative for you, and I'd like to thank you for viewing. Now it's time to fire up the virtual lab and see rule number 2 in action. My challenge to you is open the virtual lab and get the topology set up where everybody has an IBGP peering with R2. We don't have to worry about a full mesh topology again. That's what route reflectors are looking to solve, and we're not sharing any networks yet, and you don't even have to worry about configuring the route reflector. That's what we're going to cover. So get the virtual lab stood up, and then make those neighbor relationships come to life, and then join me as we go through rule number 2 of route reflector clients. I'm back on R2, and if I give it a show BGP IPv4 unicast, summary, we can see I've got my neighbor relationships here, and I'm not advertising any prefixes at this point. What we want to do is we want to advertise a network from R1 and have it bounce everywhere. So we need to make sure that R1 is a client, a route reflector client, to R2. So from R2, whoop, you got to say conf t, not cong t. We'll go to router BGP 100. I'll say neighbor 1.1.1 to modify how our neighbor relationship is going to behave. And I'll say route reflector client. Press enter. I'm going to watch the neighbor relationship bounce here for a second. Goes down, topology change. And then after just a moment, the neighbor relationship comes back to life. There it is. Hit up a couple times, show me the summary. There we go. I see that everything is back up and running. 4 messages have been sent back and forth. Now it's time to advertise a route from 1111 towards 3333 and 11111111. So what I'm going to do to make this a little bit cleaner this time is from R1, I'm going to create a new loopback address. We'll call this loopback 0, and I'll just give it an IP address of something like 15.15.15.15, mask of 255. 255, 255, 255, no shut. And that's what I want to advertise towards R3 and R11. So, jumping back to, I always type in, it's such a natural habit to me. I'm going to jump back into router BGP 100. I'm going to advertise network 15.15.15.15 with a mask of 255, 255, 255, 255. Press end. So to validate that R1 is advertising 15.15.15.15, I'll do show BGP IPv4 unicast neighbor towards 2.2.2.2. Whoop, too many dots. Advertised routes, and I see it's advertising 15.15.15.15. Let's jump over to R2, and we'll give it a show BGP IPv4 unicast summary. Looks like I'm receiving a prefix from 1.1.1.1. If I just delete the summary, we can see, well, here we go. We've got this issue again where we've got the 15.15.15 route, but there's a rib failure. Let's check out show IP route to see what's going on. And you know what the thing is? I used OSPF to grab all networks, and at this point, the OSPF route is winning because the administrative distance, 110, is lower than what BGP would advertise. So if I manipulate the OSPF distance for just a minute, we can go into router OSPF1, and I can say distance, set it to something like 201. I'll press end. Now when I check out my unicasts, now I've got the installed best route. And if I do show IP route, look at that. I now have the BGP learned route of 15.15.15.15. That's just a little troubleshooting tip for you. The administrative distance here was 200, which is 1 less than 201. But the real thing that we're here to look at is what happened on R3 and R11. Were the routes reflected towards R3 and R11? If I jump to R3, I'll do show IPv4, not R4, unicast summary. 2222 did in fact bounce a prefix towards us. And if I tap up, delete the summary, there is the 15.15.15.15. Again, there's a rib failure because OSPF administrative distance hasn't been changed at this point. But that's rule number 2 in action. Routes learned from a client will be reflected everywhere, including to non-clients. I hope this has been informative for you, and I'd like to thank you for viewing. Now it's time to talk about the third and last rule to route reflectors and route reflector clients, and that's how eBGP sessions are handled. Let's jump at the whiteboard, draw it up. So at this point, we've gotten a pretty good lay of the land as how iBGP sessions are going to be handling network advertisements with a route reflector. We've got advertisements coming in from non-clients, advertisements coming in from clients. We know how the behavior is going to act. But what happens when an advertisement comes in from an eBGP neighbor? And what does R2 do with these advertisements from iBGP with respect to eBGP? Well, that's what this nugget's all about. When an advertisement comes in from R4, an eBGP neighbor, it will be sent everywhere. This is the default behavior anyways, regardless of how route reflector clients work. And when advertisements come in from either R1 or R3 or R11, basically when advertisements come in from clients or non-clients, they'll be sent towards R4. The thing to keep in mind here is going back to that very first nuance, and that's how next hops are changed as they go along the path. As a route exits R2 towards R4, R2 is going to change the next hop to be itself. As R4 sends routes into R2, R2 is going to advertise them towards its IBGP peers, but it doesn't change the next hop unless you do something like next hop self to explicitly demonstrate that. So what we're going to do in the next nugget is we're going to fire up the virtual lab. We're going to advertise routes from R1, R3, and R4 and just verify that they're showing up in the local BGP tables. In the meantime, this has been rule number 3 of route reflectors. I hope this has been informative for you, and I'd like to thank you for viewing. And now it's time to jump in the virtual lab and make sure that we understand the third rule of how route reflectors work. In this case, they don't really do anything because eBGP behavior, it remains the same. When a route comes in from eBGP, it goes to all the iBGP neighbors. And when routes come in from iBGP, it gets advertised out to eBGP neighbors. Let's jump in the virtual lab and verify that we understand that behavior too. At this point, I've stood up our iBGP relationships. I'd challenge you to launch the virtual lab and do the same. If I do a summary real quick, not the unicast, I can see I've got my neighbor relationships here. I'm on R2. I've got 1, 3, and 11 all paired up. Let's go ahead and build a relationship now towards R4, this time being an eBGP relationship. I'll go into router BGP 100, move my mouse a little bit. We'll say neighbor is going to be, let's go out the external link 100.100.24.4. Remote AS is going to be 200. It's more common to peer based on the directly connected route when it comes to eBGP anyways. My neighbor relationship comes alive, and there we go. I've now peered with R4. If I type end and I give it a show BGP IPv4 unicast, we'll press enter here, I see that R1 is advertising a prefix of 15151515 to me. So if I go to R4, I would assume that R4 would see that NLRI being advertised out eBGP. So if I give it a show IPv4 unicast, there we go. The eBGP behavior works exactly as expected. We received the NLRI, and the next hop address has been changed to be R2's locally connected address. Now what I want to do is I'm going to give this a show IP interface brief, and I see that I have this address here, 100.245.4. This is the link between R4 and R5. I want to advertise that down to AS100. So I'm going to go into configuration mode. I'm going to go into router BGP 200, no, BGO, BGP 200. I'm going to advertise that network. It's 100.200.45.4, mask 255.255.255.0. Oh, that's not the correct mask. Let's do show IP interface, gig 00, and get the correct mask here. So right here, I see that my address is 100.245.4/29 on that interface. Let's go ahead and give that network command a run. We'll say network 100.200.45.0 because that's the network address we're talking about. The mask for a /29 is 255.255.255.248, I believe. Yeah, that's what it is. Press enter, end. Let's give it a show BGP IPv4 unicast neighbor 100.100.24.2 advertised routes. Let's make sure it's advertised. There it is. It's being advertised. We can jump over to R2, run the summary one more time. I see that I've got an advertised route here. So based on eBGP behavior of routes coming in, I should now expect to see this route at least in the BGP database for R1. Let's do show BGP IPv4 unicast. And look at that. There's the route right there. And because I had already configured next hop self to be R2, it is a valid and installed route. I can give it a show IP route, and I see the BGP learned route right here in my routing table. So that is the behavior for rule number 3 of how eBGP sessions are handled when it comes to route reflectors and route reflector clients. I hope this has been informative for you, and I'd like to thank you for viewing. Route reflectors aren't the only way that we can manage the iBGP full mesh scalability problem. There's also something called confederations. Confederations allow us to take our whole autonomous system and break it down into smaller autonomous systems that work together. You could kind of think of it like breaking down a prefix into subnets. And just like there are public IP addresses and private IP addresses, there are also public autonomous system numbers and private autonomous system numbers. So when we have a public autonomous system, like Autonomous System 300, and we want to break that down into smaller autonomous systems that service Autonomous 300, we could actually use private autonomous system numbers to build up our confederation. Let's jump on a whiteboard, and that way you can see how it really looks. Now what we're going to do is we're going to shift our view towards this section of the topology. We've been working down here in AS 100 and 200 for a while now. Now we're going to work with 200, 300, and 400. And you can see in AS 300 we have 5 routers running here. They're all running iBGP at this instance. But rather than build a full mesh towards everybody here, and make this big, really ugly, messy, multiple connection section thing going on here, what we can do actually is we can build what's called a confederation. We're going to split our autonomous system right here into 2 autonomous systems, and this is when we would use the private autonomous system numbers. Those numbers are 64,512 through 65,535 for the 16-bit autonomous systems, or for the 32-bit autonomous systems, this goes from 4,200,000,000 to 4,200,000,000. Oh, I got to Google this one more time. 4,294,967,295. These are the 32-bit private AS numbers. So in this case, we have an autonomous system here labeled 65,100 and an autonomous system here labeled 65,200. Now this begs a lot of questions about how confederations really work when it comes towards peering. The first thing that we'll say is that AS400 here and AS200 here have no idea that they are peering with a confederation. From their standpoint, when they peer right here in on these links, they are peering with AS300. These routers here know that they are in a confederation that is also representing AS300. So really what this means is when a route comes in from AS400 and it gets sent out to AS200, AS200's path, its AS path, is going to be 300, 400, and internal. Within AS300, within these confederations, however, the path will have a parentheses, and it will show the confederation path that it took to get there. Something like that. So in this case, on this router, it went through AS 65,200 and then to AS 400. Ultimately, what this means is that we can manage how many BGP sessions are actually peering with each other by minimizing how many sessions are needed. Now, only these 2 routers need to have a session, and these 2 routers can have a session, and then these 3 routers need to have a session to each other. And what's really cool is right here, we can actually use this as a route reflector. So in this scenario here, AS400 would advertise a route, and this router would think it's an eBGP peer. It would then send it outbound towards its iBGP peer, as well as up to its confederation peer. The confederation peer would kind of think of it as an eBGP advertisement, so it would send it on to this router. And maybe this router is serving as a route reflector where its client is here. So because it received this route from a non-client peer, it would forward it on to this router. And because there's an eBGP relationship here, this router would forward it on out. Isn't this all fantastic and amazing? Well, that's what we're going to jump into the virtual lab and configure in the very next nugget. In the meantime, this has been how to break down an autonomous system into a confederation. I hope this has been informative for you, and I'd like to thank you for viewing. Now it's time to jump into the virtual lab and configure a confederation. Let me bring up the diagram real quick so I can show you how we're going to tackle this task. The first thing I'm going to do is I'm going to configure our eBGP links right here. I'm going to configure R4 to try and peer with an AS300 router right here, R5. Then I'm going to configure R10 in AS400 to peer with R9 here, again, thinking it's an AS300. Once R4 and R10 have been tackled, then I'm going to start implementing our confederations here within AS300. So let's fire up the virtual lab and get going. All right, here we are. I've got MT Putty fired up here. I'm on R4, which is where I said I'm going to begin the journey. Let's go into configuration mode, This is going to be router BGP, and the autonomous system for R4 was BGP 200. So if I give this a do show IP interface brief, we can see that I am connected out gigabit Ethernet 00 towards router 5. This little third octet here represents router 4, router 5, and then the last octet is the router number itself. So if I say neighbor 100.200.45.5, the remote autonomous system in this case is going to be 300 because R4 doesn't know or care about the confederation. The confederation is going to serve AS300, so this will be a valid configuration on R4. Similarly, I'm going to jump to the other side of the topology, and I'm going to configure R10. So we'll go router BGP, and in this case, it was servicing autonomous system 400. If I give it a do show IP interface brief, it is addressed out fast Ethernet 40 towards R9. So we'll say my neighbor is going to be 150.150.90.9, and the remote autonomous system, again, is going to be autonomous system 300. So this establishes our external peers for the confederation. Now we need to start building the confederation, and I'm going to start with R5 to get that done. This is what's connected directly to R4, and here's how we configure it. We'll go into configuration mode, and then we'll specify router BGP. And what we're specifying here isn't AS300. We're going to specify our confederation number, which is also known as a member ASN. The autonomous systems that make up a confederation are called member ASs. And the member ASNs are usually the private autonomous system numbers. So our autonomous system in this case, for R5, was 65,100. But then we can tell our BGP instance that we are servicing a confederation with BGP, confederation, identifier, and then we say 300. If we draw out the topology real quick, we had R4, which was AS200. Then it connected to R5, which serviced AS300, but it was in AS65100. It also peered with R8 down here. And I'm going to put a little dotted line here. This is where 65,200 is. For these routers, they're inside the autonomous system, but serve as a connecting link between member ASs. We have to specify who our peer confederation members are. So in this case, we're on R5. We've now identified that our autonomous system is 65,100, but our confederation ID is 300. Now we have to tell R5, hey, it's okay to peer with 65,200. So the command to do that is BGP confederation peers, and then we can say 65,200. So now on R8, when R8 and R5 initiate a connection to each other, they'll be able to look at the remote autonomous system and quickly identify if this is just a peer in the confederation or if this is a true external BGP configuration. So now what I'm going to do is I'm going to give it a do show IP interface brief, and we'll take a look at the addressing for our peers that we need to configure. First, I'll build the iBGP connection within the member AS towards R6. We'll say the remote AS is our own AS. And then I'll build the peer connection towards our confederation peer, specifying the remote AS is 65,200. Let's jump down to R8 and configure our confederation peer on this side. I'll say router BGP, and in this case, it's going to be 65,200. We'll specify that this is a confederation identifier of 300, so it knows that it's servicing the 300 autonomous system externally. Then we'll specify our BGP confederation peer is 65,100. I can bring up the neighbor relationship now with 10.0.58.6, and the remote AS is 65,100. Nope, that's wrong. I typed that wrong. It's not 10.0.58.6. It's 10.0.58.5. Some days you just can't type. There we go. Neighbor statement 10.0.58.5, remote autonomous system, 65,100. And there it is. The neighbor relationship comes up. While I'm here, I'll also specify my neighbor relationship of 10.0.89.9. The remote AS is our own autonomous system. And now we can finish configuring the rest of these items here. I'll jump to R6. We'll go into router BGP 65,100. Again, we'll specify this is in a confederation and it's servicing AS300. Oop, typo. I'll bring up the neighbor relationship with router 5 here. The neighbor relationship comes up. I'll also go ahead and specify I want my other outbound neighbor here, router 7, also an internal BGP session. And if you recall, the topology looked like this. There was R5, there was R6, and there was R7. What do we know about IBGP relationships in this scenario is that they won't forward prefixes unless we configure a route reflector. So truthfully, in this scenario, there's nothing harmful about configuring either of these as a client, so we know for sure that routes get bounced in both directions. So that's what I'll do. I'll specify my neighbor of 10.0.56.5 as a route reflector client. Then I'll do the same for router 7. I'll say route reflector client, and now I'll jump over to router 7 here and get it stood up. We'll say router BGP 65,100. Making sure to specify this is in the confederation servicing AS300, and R7 serves as an edge towards the other confederation peer. So I'll say BGP confederation peers 65,200. I'll bring up the neighbor relationship with R6, and I'll start building the relationship between R9. We'll specify it in the remote AS of 65,200, the confederation peer. The last router that we need to configure is R9, which will have 3 neighbor relationships. The eBGP relationship to R10, the iBGP relationship to R8, and then the confederation peering relationship to R7. Let's go into BGP 65,200. Tell it that this is in a confederation servicing AS300. And because this is a confederation edge peer, we're going to specify the peers of 65,100. If I give it a do show IP interface brief, just to get my lay of the land, we'll start by bringing up our eBGP relationship out FA 4/0. The remote AS was 400. We'll bring up the iBGP relationship with R8. That was in 65,200. And then lastly, we'll bring up the confederation relationship with R7, and that was in remote AS 65,100. Looks like debug was on there for a second, so I went ahead and turned debugging off, and now from R9, I can give it a show BGP IPv4 unicast summary, and it tells me that I must have typed something wrong because my neighbor relationship with router 8 isn't coming up. It tells me that the peer is in the wrong AS. So that means I might have typed something wrong here. If I give it a show run section router, yep, sure enough, I am declaring here that my R9 connection here was in 65,100 when it wasn't. Let's go ahead and fix that in R8. Let's do router BGP 65,200, no neighbor 10.0.89.9, neighbor 10.0.89.9, remote AS 65,200. And now the neighbor adjacency comes up. So now back on R9, if I give this a show IP BGP summary, I see that I have my eBGP relationship here going towards AS400, my iBGP relationship here in AS 65,200, and my confederation peer relationship AS 65,100. Let's now introduce a route from R10 into our BGP environment. If I go into configuration mode, router BGP 400, we'll specify the network statement of 10.10.10.10, a mask of 255.255.255.255, so that we can inject the loopback address into BGP. Now the NLRI is coming in from R10. We see that we've got a prefix received, and if I give it a show BGP IPv4 unicast, we see that this route has made it into our BGP with the next hop address of R10's address. Now we know about the behavior of iBGP and eBGP. Let's jump up to the confederation peer of R7 and give it a show BGP IPv4 unicast to see how it's behaving. As expected, it doesn't change the next hop address. Even though this is coming from a different autonomous system, because it's in a confederation, it still behaves like IGP in that regard. Notice the path too. Like we said, this came from AS 65,200, then it went to AS 400, then it was originated internally from there. So let's go to R9, go into router BGP 65,200, specify for our neighbor 10.0.79.7. Let's set the next hop address to be self. Exiting out of configuration mode, I'll jump back to R7, we'll refresh this, and after a few seconds, we do end up getting the correct next hop address, and it's installed in the routing table. So if I give it a show IP route, I see now that I have a route to 10.10.10.10 via router 9. Now we would expect, in this case, if we've got R7, who's got the route coming in from R9, then we've got R6 and R5. Because R6 is serving as a route reflector for each of these, R7 is going to advertise this to R6, who's then going to reflect it to R5. But the issue here is this, again, is IBGP, and we're not changing the next hop address. The next hop address is 10.0.79.9, which R7 does have a connected interface on. However, here's another thing to think about, is that these are all in the same autonomous system, 65,100. And it is pretty likely that all of these devices would be running an interior gateway protocol like OSPF or IE-IGRP. So to solve another next hop problem that you may run into, we could configure OSPF between R5, R6, and R7. Let's do that. We'll just do this really lazy, OSPF 1, network 0.0.0.0, 0.0.0.0, area 0. I can do a do show history, and I'll just grab this section right here. We'll go to R6, config T, paste it, R5, and paste it. And after just a moment, OSPF converges. So now what I'm going to do is I'm going to go over to R6. I'm going to exit out of configuration mode. I'll give it a show BGP IPv4 unicast. And look, there's the route 10.10.10.10 that came in from R7, valid next hop, because it knows about how to get to this network from OSPF. This should have then reflected this route off of R6 to R5. If I go to R5 now, and show BGP IPv4 unicast, look at that. There it is. Now, lastly, the behavior is that R5 would have advertised this network out through eBGP to R4, but changing the next hop address. Let's go to R4, jump back into privilege mode, show BGP IPv4 unicast, and there's nothing there. Why is there nothing there? Because I forgot to configure the neighbor relationship with R4 on R5. Okay, all over the place today. Let's go router BGP 65,100, neighbor 100.200.45.4, remote AS is 200. Remote AS is 200 for real this time. Neighbor relationship comes up. Now if I go to R4, there it is. There's the route to 10.10.10.10. So by using a confederation, we got around the IBGP full mesh mandatory statements to make all this work in AS300 by splitting it up into a couple confederation ASs. Now, when a route came in through AS400, we were able to send it up into AS65100 from AS65200 because this AS was running an interior gateway protocol as well as had a route reflector. The IBGP route was sent all the way through, and then the eBGP rules state that we sent it outbound towards AS200 with a new next hop. So that's confederations in action. I hope this has been informative for you, and I'd like to thank you for viewing. And there you have it. BGP scalability issues, particularly with IBGP, have now been solved because we have learned about multi-hop, we've learned about route reflectors and the 3 rules that make up route reflectors, and then we took it a step further and dug into confederations. So that's been handling scalability issues, especially with IBGP. I hope this has been informative for you. I'd like to thank you for viewing.